Thank you very much. Very good morning from IIST Trivandrum. Today I thought, I will take you to our journey to our nearest star, the sun. Although originally we were also probably planning to have a solar system study lecture, but then I felt that, within a 1 hour, it will not be fair to cover all the solar system bodies. But let me focus on our nearest star and the star-Earth interaction and other planet interaction I will briefly talk about, which is also very, very important. So before I move on, as you heard that, I am just representing the Aditya L-1 Science Working Group. But you please be also aware that this is a indigenous mission from India, a good example of Atmanirbhar Bharat, because you will see that all the payloads have been developed at different institutions, academic institutions, and different ISRO centers within the country. And you see the different logos at the bottom of my slide, which represents the participation from different institutions across for science and some science, payload development and operations as well. So before I go into the subject, I will also take this opportunity to just introduce, this institute where I am, talking about. It's called Indian Institute of Space Science and Technology. This is an academic wing of our Department of Space. And I again take this opportunity to also highlight that there are different academic programs in this university which is dedicated for space. And since I'm interacting today with majorly teachers. So it will be good that, if the teachers also are aware of these institutions, capabilities. So we do run many different programs, starting from an undergraduate program to a dual degree in physics and astronomy, then master's degree, different master degree programs. And we have 400 plus PhD students. 200 are regular PhD students who are on campus, but there are 200 odd scientists from different ISRO centers. They are also performing their PhD with an IIST collaboration. So that's again a real fleet for IIST. There are different post-graduation program across our departments and within the engineering and our science and humanities department as well. So the other major thing which I want to just very briefly highlight, that the key of IIST is this multidisciplinary nature of the research and what we call today as experiential learning. The students get a direct opportunity to work in the lab with the payload development, and those payloads eventually fly into space with next generation missions. So whether you call any today's focus missions, which is of national mission of importance, whether you call quantum technology, whether you call AI ML, whether you call nanosciences, you name it, 5G, 6G development, IIST is one of the nodal institute in the country. Along with the major IITs and IISC, IIST is also the privilege to be part of the national missions for majority of the programs. So I just have just very quickly highlighted these all different small little blocks here, which represents that we are part of this high quality research at IIST. So teachers across the schools, be aware that the budding youngsters who are looking for opportunities for their future in the space domain, particularly IIST is probably the first stop. Just one slide that IIST students, participate in this particular small spacecraft system and payload center. This is a representation of our experiential learning. Our undergraduate studies, they built these payloads. This has been launched with our InSparsat PSLV C52 around February 22. Now what is happening is every 6 months almost, there is an opportunity with our ISRO, which is called a POEM platform. And there the different academic institutions can also participate in giving small little payloads. And IIST gets this opportunity every 6 months to fly their own indigenously developed payload. The other interesting aspect is we fly the payload, And we also, control the spacecraft and in terms of the data telemetry and all that from our own ground stations. So we have a ground station in campus, which our students after post dinner, when there is a line of sight available, they will go and talk to the satellite, take the data download, and work with the data which they have, the instruments they have built. So this kind of opportunity, I don't think exists anywhere, within this part of the globe. So I think this is a unique institution. So for all the teachers, if you have further questions about IST's capabilities and different career opportunities, please do contact me. I will be happy to interact with you. Now I come to my star, which is the sun. So sun in our solar system, it's a middle-aged star. It's in the middle of its lifestyle or lifespan, but it is a spatial star because it is the only star on which we can resolve spatial scales on which fundamental processes take place. So I will show you many pictures and movies which will give you indications that on the surface and on the atmosphere of this star, we are able to see presence of different structures. Of course, it is special because it provides almost all the energy to the earth. Our existence, our life is just because of the presence of the sun at an appropriate distance away from our planet. It is also a special star because it provides a unique laboratory in which to learn about various branches of physics. As you heard, that I am actually trained in only physics up to my master's level. So I only stepped into astrophysics after I joined for the PhD program. So I often try to highlight that astrophysics is not a different branch. It is actually an extension or application of physics, and I chose within astrophysics again sun as a star, and I tried to do all my curiosity about physics through this particular object. And if you just talk about any small little things in terms of you want to learn the understanding of turbulence in the universe or even in our nature, everything is actually, the medium is turbulent. So if you want to study the turbulence, if you want to study the generation of the magnetic field, how magnetic field is generated in nature, there is a process called dynamo. So all these are actually directly applicable to the solar observational studies. 99.9% of the universe is actually in the plasma state. We have three states of gas, liquid, and which undergoes a phase transition. And the fourth state of matter is plasma. So in the universe, since the temperature is very high in majority of the astrophysical systems, the material is all in the plasma state. Of course, sun is actually at the plasma blob, which is there at appropriate distance away again. So if you want to study the plasma physics properties, that's your ideal laboratory. You talk about atomic and molecular physics. There are different transitions in atomic states, similar with the molecular domain as well. So if you want to apply your knowledge of atomic physics and molecular physics, you need a laboratory, you need certain spectra, and these spectra is coming from the stars. So what we do is we can't go reach the star. We only observe the light which is coming from the star, and that light we analyze through the spectrum. And through the spectrum, studying the different spectral line properties, we try to say what is the source of this particular light, where it is coming from. So a lot of knowledge about atomic physics or molecular physics is again we are doing it with the context of the sun. There are many more fundamental physics questions like neutrinos. Neutrinos were originally, the particle physics domain was considered to be massless. There were no mass of the neutrinos were considered. But there were experiments on the sun, namely the solar neutrino experiment, that revealed that neutrinos undergoes a transformation, and that transformation is only possible if you have a small little mass of neutrinos. So there were different type of neutrino flavors were observed, electron neutrinos, tau neutrinos, and so on. And then this kind of problem was finally resolved. Uh, Fundamental problem of gravitation the light bends because of the presence of a gravitating object was again done during the total solar eclipse experiment. So I can just say, this way, sun really has provided an ideal laboratory to, understanding the various branches of physics itself. And there is a new branch which is called the space weather, and this also deals with the sun and earth relation. As I mentioned, today our life is because of the presence of the sun, and now our life, day-to-day life, is so much dependent on the assets in the space, namely the satellites and other assets as well. We are talking about just going to the International Space Station. We are still delayed a little bit because of certain technical glitches, but all these are heavily dependent on the solar conditions. If there is a huge storm in the sun, that will actually affect our sun earth environment, and then launch actually would be very dangerous at that point of time. So today all the satellite communication system, satellite operations are crucially dependent on the this sun earth coupling system, which is completely governed by whether there are dynamic solar events happening on the solar atmosphere or not. And that's a short-term effect. Also, if sun doesn't radiate the same amount of energy what it is radiating today, it will, of course, our climate will be affected. We are our climate balance is definitely, it's completely controlled by the total solar radiation, and the forcing of the sun dictates our climate. If we go back to our historical records for different several thousands of years, we find many mini ice ages. And now we know that these ice ages are directly influenced because sun was not dynamically or magnetically not so active during those phases. So it is very important for us to understand how sun is behaving in a long term, in terms of its total energy output and so on. So that directly affects our climate. So all these are very, very important area of understanding our presence and our assets in the space. That is one of the reason I'm just talking about today Aditya mission. That Aditya mission, we have several scientific payloads that is going to address some of these questions scientifically as well. And in a larger context, that in the astrophysical context, phenomena happening all over the universe can be best studied at a close distance, where the relevant physical processes are taking place, and because we can really resolve it. Same actually true with the planets as well. And to be honest, in recent years, and you can see that the planetary missions, and particularly from Indian context, that next 10, 15 years, we have several planetary missions in pipeline. We are planning to go back to moon. We want to take samples back from moon and study the lunar content of water and other minerals and so on, if any. And then we want to rover again in the moon. We want to go to Venus. We want to understand the Venus atmosphere. So this rejuvenating about the study of the solar planets and the sun and the solar system is actually a new phenomena. And particularly from Indian context, I must point out that our Vikshit Bharat 2047, the timeline and the different objectives which has been set is completely driven by our near Earth environment and the solar system environment, where we are planning our own space station. We are planning to go moon a number of times. We want to land in moon, but before we could do that, we will have our own Gaganyaan mission, many different phases. We'll have unmanned missions, and then we'll have a manned mission eventually to land in moon and return back. So all these demands, basic understanding of the solar system and the sun planet interactions and the solar activity as well. So this magnetic activity is just not a phenomena which is there only in the sun. We now know there are innumerable amounts of stars, and then other accretion disk and other astrophysical phenomena. The magnetic field actually plays a very, very important role, and that's what is also very, very important. And if one talks about also other techniques of astronomy, whether it is radio astronomy, there are lots of mathematical developmental model development in terms of the understanding of the radiation which comes from long distances and so on. All these has been first experimented in the case of the sun, and then it has been expanded to astrophysical scenario. So what I'm trying to highlight is people think that the sun is our nearest star. It's a pretty old-fashioned probably object to look at. This has been looked at for hundreds of years, but still it has its most importance for even further understanding the more fancier astrophysical object to study as well. So that way, sun really plays a very important role. This is the internal structure of the sun, where in the interior, this energy is generated through a thermonuclear reaction process. Hydrogen gets converted to helium, and then we have 700 million tons of hydrogen gets burning there every second. Then we have about 30% inside this area we call the radiative zone. Energy is primarily transported by radiation. As you can see here, there is these random walk of the photons. Although the photons travel at the speed of the light, they bounce so many times through this dense material. They use about 1 million years to finally escape from the sun. So this is like a drunken man moving into space and colliding with another companion. So this is the area which we call radiative zone, and then we have the final 30% inside the sun. We call it convection zone, where energy is transported by convection. It is just like boiling a soup. We put a bowl of soup in a source of heat. Then initially, the small little bubbles which will form. The hot material will come up to the top, and the cold material is heavier. It will go back to the sink to the bottom, and then it sets a circulation, which is called the convection. And inside the sun, that's actually a full convection zone underneath the surface of the sun. As I indicated, that we know that there are different kind of variability which is now observed in the sun. What I'm showing here is a movie taken from Solar Dynamic Observatory. It's a NASA mission which is looking at the atmosphere of the sun, and I'm showing you a region on the sun. These are called active region, which you see comparatively brighter as compared to the other neighboring regions. The reason why these regions are brighter is because of the presence of magnetic field. And because of the strong presence of magnetic field, the material is actually confined. So these are a confinement of plasma material here. And because of certain instability, they are there for many days. But suddenly, because of certain instability, these huge structures we call coronal loop structures, they can actually erupt. And when they erupt, these materials will be thrown into the interplanetary space. Some of it may go back and then again fall on the surface. You will see again additional heating and so on. But the material which is thrown into the interplanetary space, they will travel. And if you are moving around, you or any satellite, that is going to be impacted by these material which is thrown out of the sun. So we really need to worry about these huge explosions which happens in the sun. These are also called solar storms. We need to understand when such a storm can likely to happen, and if such a storm happens, how strong the storm is, and what would be the final impact if we are actually in space at that point of time. So that's a kind of variability which I was talking about. And this is because of the presence of the magnetic field on the surface. I will show you these regions are called sunspot regions. So sunspots are seen for the last 400 years. And now we know that the sunspots come in opposite pairs, and they're connected by these kind of huge loop kind of structures. And these loop kind of structures can become unstable. And then when they become unstable, then these material which is confined within the loop system will erupt, and the plasma will be thrown into interplanetary space. So these are also related to a phenomena called flares in the sun, which again, also accelerate the particles, and these particles will be traveling and impacting with this. So that's one kind of short-term variability. And the other long-term variability, which I was referring to, is that some days, you will find on the surface of the sun there are these sunspots, but there could be some period where there are no sunspots at all for months and years. If that happens, we call them as a quiet phase of the sun. And this is the active phase when you have many more sunspots. So these are long-term effects, which has fundamentally linkage to our climatic research. So that's again another domain which we called it space climate. So what is called the space weather? That means our immediate time scales of hours to days, how to predict what is the space near Earth environment. The other is called space climate because of the long-term variability changes in the sun, whether it impacts our global pattern of our climate. We do see there is a global warming and so on. Whether global warming has any effect because of the certain thing happening in the sun, this is also another domain of research what we work on. So here again, I'm showing another movie from taken from NASA satellites. Again, you see a huge explosion in the sun. These eruptions, which leads to coronal mass ejection, a huge amount of material will be thrown out, and then we need to worry about when these things are seen. So that's the short-term variability. This is the long-term variability which I was referring to. What is plotted here is yearly sunspot number for last 400 years. What you see here is that seems to be a sinusoidal typical sort of periodicity of 11 years, where it shows that certain period you have many sunspots. We call it sunspot maxima, solar maxima. There are periods where there are few sunspots. There could be some periods where there are no sunspots at all. There were actually historical records reveal that between 1650 to 1700, there were no sunspots recorded. What was the effect of that? The Volga River, which runs into the major part of the Europe, was frozen for 40 years. People were actually skating on the River Thames in London, even in summer. So the water was frozen. That means it was extremely cold. And as I indicated also previously, that these mini ice ages and all that is all now linked with this, this particular state of affair. This is again a recent movie taken from the Parker Solar Probe, and you see a CME which is ejected out of the sun. You see even the Milky Way in the background. And I'm sure from this movie you can make out that this is not a very pleasant environment to move around. And this is the actually state of affair of the space weather. And we really need to predict when such a big storm will happen in the sun. Here again, I'm showing another movie where it shows that there is a something coming out of the sun, very close to the sun. Then this is extended part of the solar corona. We call it heliosphere. Is the extended sun-Earth system together, and beyond we call it as heliosphere. And then eventually these huge ejecta, when they travel between the sun-Earth distance, and then eventually here we are, which will impact us. We need to worry about how much energy these guys are carrying, what sort of magnetic field these fellows are carrying, because they are also interacting with Earth's magnetic field as well. So there are a lot of interactions we have to study in terms of these solar storms. So this is what is meant for space weather. And as I indicated, that our life is very much dependent on space assets. Whether we talk about astronaut safety, Shukla is going to International Space Station. If we want to do some experiment just around the docking time, if there is a huge solar storm, you can imagine the life is not going to be very easy. So we have to predict when such solar storm happens. And then, of course, that time has to be avoided for any activity for the astronauts' safety. Our satellites, their primary source for all our communication, whether you call it GPS, whether you call it 5G, 6G network, whether you call our satellites which are maintaining our surveillance system, defense system, everything is actually going to be affected if there is a huge storm in the sun. And this is happening, and there are lots of hundreds of satellites have been actually damaged or destroyed because of the solar storm. Not many people are in the private public knowledge is aware of that. But today, all the space industries are aware of that. All government agencies are aware of that. So space weather is actually a big threat for our modern day technology. It does affects our telecommunication. It affects our GPS and network. It affects our air traffic system. Suppose you take a long haul flight from Delhi all the way to New York. Now, it doesn't go through a low latitude like European countries. It takes a polar route. And when you take a polar route, if a huge storm happens at the sun, these particles normally, because of the Earth's magnetic field, we are protected at the low latitude. But they can actually come through the polar region. And if you are taking a flight, you are getting exposure of these solar energetic particles and cosmic rays directly. So your body is bombarded with this. So air traffic needs to be actually controlled or monitored when such a solar storm is happening. Satellite health and lifetime. As I mentioned already, the satellites are getting damaged. Their lifetimes are shortened because of this. There was a recent phenomena. The SpaceX, launched 40 odd satellite, and there was a solar storm, and Mr. X ignored the warning, and he lost 39 satellites because there were enhanced atmospheric drag. When a satellite moves into the space, there are a lot of calculation in terms of the trajectory of the or the orbit of the satellite, and there it is at some atmospheric drag conditions are put into your equations. But then if the atmospheric conditions, the density profile, everything changes, the drag also will change. So the atmospheric drag, if it is changed, then what happened for this SpaceX launch was the satellites which were supposed to go to 400 odd kilometers, they never could reach actually beyond 250 odd, and they all fell flat and they were destroyed in the lower Earth environment as well. So there are n number of such applications where space weather is actually a very, very important point. And as I was indicating, these highly energetic particles, if they penetrate our Earth's magnetic shield, then they will also interact with our power transformer systems. They induce currents, and those currents will damage the transformer. So the electric power grids. Then there are people who are engaged in oil pipeline, work, and the oil pipeline work is crucially dependent on the GPS coordinates and on a millisecond accuracies almost. And if that gets affected, then your entire operations will be completely disrupted. So there are many such areas where space weather is a real big event. So with all that, we had our own mission, Aditya. We were live from Sri Harikota, Andhra Pradesh, in September 23. You see a little movie of that. I will not run the full movie here, but you can probably see a little part of it.
Spacecraft preparation facility. This is the Aditya L-1 spacecraft being prepared and ensconced into a protective container where the environment is controlled and the temperature is controlled, the cleanliness is controlled. At the vehicle assembly building, again, there is a clean room provision to safely integrate it to the rocket, and then the heat shield halves are closed. Now the vehicle is fully ready to be moved to the launch pad, which is about 900 meters away. This is PSL. The mission intends to place the spacecraft in 235 by 19,500 kilometers orbit with an inclination of 19.2 degrees. The total mission duration will.
So here you see several thousand people actually was there in the public gallery. This is just the countdown started.
Aditya L1, Surya ka aate hain. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
There's a beautiful lift off.
5 seconds. Normal. You are tracking? PT tracking. Magnificent liftoff of PSLV C-57 with Aditya L1 on board. Plus 15 seconds.
PSLV-C 57 का सफल उत्थापन और इसके साथ प्रथम भारतीय सौर अंतरिक्ष यान निकल चुका है सूर्य के तेज से विज्ञान को प्रकाश करने। इसके साथ ही एक और कदम है अंतर्ग्रहीय सफर में भारत की उपस्थिति सिद्ध करने का। आप देख रहे हैं PSLV-C 57।
Okay, so that's what's sort of a four stages of separations, and eventually it was one of the unique, journey, because as you know that Lagrange one mission is a long journey, and here there was separation after almost an hour. So this is quite unique in its own right. Uh, Lagrange one is a quite a unique position. This is almost a sort of a location where the satellite is actually orbiting around a very large halo orbit. And for this orbit, movement, you need a centrifugal force, and that force is actually provided by the force balance between the satellite and the Earth and the satellite and the Sun. So once you reach Lagrange one, then you have a continuous view of the Sun, and you actually do not have to use much fuel, because this force balance is allowing you to be in this orbit for a very, very long period of time. So for solar missions, Lagrange 1 particularly is a very, very good vantage point. And the other thing is, anything happening in the sun before it reaches Earth, if there is a CME traveling towards Earth, it has to pass through the Lagrange 1 location. So if we are there with the in situ instruments, then we will be able to study the properties of these huge, say, magnetic cloud, which is passing through the satellite, and then we'll be able to probe its kind of a charge, what kind of material, what kind of energy it has, what kind of magnetic field it has. So these are called in situ measurement. And other thing is called remote sensing, that we are there at Lagrange 1. We're looking always to the sun, and we are taking images in the sun, and also measuring the energy output in terms of the X-rays and other wave bands. So this was the trajectory to L1. We were, doing a five Earth-centered orbit transfer, and then around 20th of September, we took off this Art Center, and then there was a cruise phase, pretty long, about 3 months, and then there was a Lagrange insertion. And this was even, some of the payloads what we have, or experiments which we opened up to detect these charges, or the counts were recorded, just to ensure that, we are doing good. So that's the insertion. And as you see here from this was a small little maneuver for only few seconds. And this was such a precision maneuver which has happened, and ISRO can be very, very proud of, because apart from NASA and ESA, we are only the, a third nation which we could actually do a perfect L1 insertion, and it was so well done that we could go around in the Lagrange one with last more than a year of operation, absolutely with very less amount of fuel. Although originally the mission was only envisaged for 5 years, so what I understand that the amount of fuel saved by this precision insertion, that we can be there at least for 10 years. So that's again a big success story of our research organization. For the realization, there were scientific payloads, as I indicated. So this movie will give you an oversight.
Carries a suite of 7 scientific payloads to carry out systematic study of the sun. The Visible Emission Line Coronagraph, VELC, studies the solar corona and dynamics of coronal mass ejections. The Solar Ultraviolet Imaging Telescope, SUIT payload, images the solar disk in near ultraviolet and also measures the solar irradiance variations. The Aditya Solar Wind Particle Experiment, aspects, and plasma analyzer package for Aditya, PAPA payloads study the solar wind and energetic ions, as well as their energy distribution. The Solar Low Energy X-ray Spectrometer, SOLEXIS, and the High Energy L-1 Orbiting X-ray Spectrometer, Helios, study the X-ray flares from Sun over a wide energy range. The magnetometer payload is intended to measure the interplanetary magnetic field at the L1 point. The science payloads of Aditya L-1 are indigenously developed by different laboratories in the country. VELC is developed at the Indian Institute of Astrophysics, Bengaluru, Suit Instrument at Inter-University Center for Astronomy and Astrophysics, Pune, Aspects Instrument at Physical Research Laboratory, Ahmedabad, Papa Payload at Space Physics Laboratory, Vikram Sarabhai Space Center, Thiruvananthapuram, Solexis and Helios payloads at UR Rao Satellite Center, Bengaluru, and the magnetometer payload at the Laboratory for Electro-Optic Systems, URSC.
So, as I was indicating, it's a combination of in situ and remote sensing instrument. We have this ultraviolet imaging telescope, the coronagraph, which blocks the solar disk, and you see the outer atmosphere, namely the inner corona part. We have two X-ray spectrometers, one looking at a high energy and the other one is looking at a low energy. At L1, we have in situ measurement in terms of these particle detectors called PAPA and aspects, and the magnetometer, which is also characterizing the properties of these huge magnetic cloud. When it travels from the sun, before it reaches Earth, it will travel through Lagrange one location, and we will be able to probe the properties of these magnetic cloud through these in situ measurements as well. As I indicated earlier, the Earth has its own magnetic field, and this is the Earth's magnetosphere. This is not symmetric now because of the presence of the sun and and the the particles which come from the sun in the form of these kind of ejecta, and also a continuous flow of particles comes in the form of a solar wind, and that disturbs our magnetic field, and that's the kind of structure what we have here. But when a huge storm will come, this structure will also change a little bit, and the particles can escape these shield and get into the Earth's environment as well. So we can be affected very badly if these huge storms happen on the sun. Of course, there are many satellites which are roaming around outside these Earth's magnetosphere, and they get directly affected by these big magnetic cloud, and that's what I was talking about, the space weather effect. These are the different instruments situated at different body parts of the satellite, the coronagraph, and the imaging telescope. This is the first image, the current view of the coronagraph instrument. Some of these results are now published in the international journals. You see, we are able to see these magnetic structures with the spectroscopic capability of getting an estimate about their temperature, about their evolution. And as you see, these kind of structures eventually erupt, and then they give rise to the CMEs and so on. So we do have regular observation from this coronagraph. Now we have our ultraviolet imaging telescope, which has many different filters to look at different atmospheric layers of the sun. This was the entrance aperture door, which was opened. These are the first light images which we took. We have this sunspot region. We have surrounding region called plages, and these regions are so-called quiet sun. We have many different filters which are probing the different layers of the atmosphere of the sun. And as you see here from these images, these are first light images, early images from the Suit instrument, different filter of chromospheric heights of the sun. And we can study all these different effects of the sunspot evolution and so on by looking at these different images. Here again, you see that we are taking these images every few seconds, and then you can get a different atmospheric heights and their properties, how these kind of structures are evolving as well. When such an eruption happens very close to the sun, here again I'm showing example of these eruptions as captured from the Suit instrument. So there was a huge flare which gives rise to a coronal mass ejection, and this early structure of the coronal mass ejections have been captured by this instrument. This is the X-ray experiment I was talking about, one looking at the very low energy component. We look at sun as a star. So this is the integrated flux from the sun, and you see these huge spikes. These huge spikes corresponds to the solar X-rays. We are comparing our results with American, satellites for our validation and so on. Here again, another event with the high energy X-ray spectrometer. You see very nicely the green curves are showing the flux increase. So the timing of the flares and the duration of the flares, all these properties we can really, see it very well. Again, last year there was a very amazing thing happened, that normally X class flare happens once in a lifetime, and sometimes several years there may not be X class flares, but within 1 week there were so many X class flares happened in the sun. And we captured all these X class flares. There are lots of scientific work is happening on that. What is the effect of these X class flares on the CMEs, and then the CME impact on the so these X-class flares were recorded from our low energy X-ray spectrometer and also the Helios X-ray spectrometer. You see these huge spikes here. They all corresponds to, we call it X-class, the highest class of flares so far detected in our lifetime. When these huge flare and the CME travel through interplanetary space, when it reaches the Aditya L-1 spacecraft, it captures the magnetic field changes carried by these magnetic clouds. So here you see the record of our magnetometer, and very nicely it captured. Normally you are seeing, there is hardly any magnetic field in the interplanetary magnetic field environment. And then suddenly when a huge, magnetic cloud travels, we can capture the magnetic field content of these clouds, because this is a very important quantification, will allow us to understand when it impacts with a satellite or any other space assets, or in our near earth magnetosphere, what would be the kind of impact and so on. So this is again a recent paper published in the highest quality astrophysical journal letter. We are showing that this is the first multi-payload science from Aditya L1. Means, we use the X-ray, data, we use the near UV data, and we combine all these data to get a better understanding about where this flare is coming from on the sun, this particular location, the sunspot area, how with time it was evolving, and then with the X-ray flux, what you see here, how it is changing. So this is the American satellite GOES comparison with their, the American again, another satellite called Solar Dynamic Observatory. So we compare our results with the national, internationally available data sources to validate and showcase that how our observations is giving a new insight about understanding of these huge storms which happens in the sun. Because when you have a comprehensive understanding, that will only allow you to do a better space weather modeling and so on. I would like to again highlight, this is another particular cell called Aditya L1 support cell, which is essentially done for training of the users. So since I am expecting a lot of teachers here, that this is again an opportunity for you. We do conduct workshops for undergraduate student, postgraduate student, PhD student, and also for teachers, so that the teachers get a first-hand experience with the Aditya L1 data. And if somebody wants to do some little bit of science research, that is also possible. So please do look for in the Google search the Aditya L1 support cell activities. This is the QR. You can find out when is the next workshop, and you can always contact the Aditya L1 support cell for any understanding. What I want to highlight here in this particular slide is, again, this is the Sun-Earth system. Of course, there is Sun, there is Earth, Earth's magnetosphere. And as you can see here, internationally, globally, there are many, and this is an ideal location to really study the Sun-Earth impact. There are many, many satellites, of course, from other agencies as well, but being at L1 with our unique, system of new instruments, is really giving us a new opportunity to understand the heliophysics. So I think we are in the golden era of an Indian space program, and it's also truly for Sun-Earth system understanding. Solar missions and planetary missions are going to really, really give us a new avenue for participating. I will also very briefly point out that we are sometimes also participating in international program. This is a very unique experiment from European Space Agency. What this is trying to achieve is again the coronographic images. What is happening is here, there is a two satellite, this is a twin satellite. They were docked together. They were launched from our own PSLV launcher in December last year, and they went into the space. They undocked in themselves, and in space they are creating a formation flight configuration. So what it is doing is the separation is about 150 meters. This particular satellite is casting a shadow of the sun, what we normally achieve with the total solar eclipse. So this is the umbral shadow here, and here it is able to block the solar disk light and taking the images of the corona. So that instrument is called a coronagraph instrument. That instrument we do have in Aditya, but artificially we block the solar disk within a telescope. Here, naturally, it is trying to cast a shadow by this formation flying experiment. So this is again a very, very unique experiment in space. It is very in technologically, it is similar to our docking experiment, which has happened very recently. Very similar experiment for European Space Agency with a slightly different technological demands. And we are also participating in that experiment. We will see actually the results probably in next 1 or 2 weeks of the first light of how beautiful these images are in the public domain. So this is my last but one slide. It is my lifetime, I would say, dream come true to be able to see our last 20 years of dream of having our own mission, building this instrument with participation of large number of Indian colleagues at different parts of India, and being part of this launch at that day in the control center along with my colleagues is will be the probably my lifetime moment. Thank you for all your attention. As it was indicated, I was at Aryabhatta Research Institute. This is a picture taken of the Himalayas from our observatory with my mobile phone. So please do visit, Nainital, which hosts currently the two largest optical telescope from this part of the globe. So I think we are in a golden era with the ground-based facilities and space-based platform to look at our Sun-Earth system and the planetary system. Thank you for all your attention, and I'm ready for taking questions.